Good morning students. Today is the lecture 4 under module 2. In this particular lecture, we will discuss about the inorganic membranes and the materials that is required to prepare inorganic membranes, their advantages and disadvantages. So, as you know that we have been discussing the membrane materials since last class. Today, we will wind up this particular discussion, and the next class onwards we will move ahead with the module design and their merits and demerits. As you know that membrane based separation processes are widely used in our day to day activities. Polymeric membrane is one of the most important and widely recognized membranes used for water and wastewater treatment as well as many other applications. Now, these polymeric membranes are however associated with some problems like permeability, selectivity, scaling or fouling problem, back flushing. Then in desalination usually we need a very high pressure. So, sometimes membranes get distorted, then it cannot withstand higher temperature applications. pH, whether a very high acidic or high base pH is not good for polymeric membranes, then various corrosive environment they are not able to withstand. And these are some of the inherent problems which are associated with polymeric membranes. Due to all these problems, the membrane scientists have taken a keen interest to develop ceramic membranes. So, polymeric membranes have also low mechanical stability and fouling problems. Mainly to overcome these things, membrane scientists have looked into inorganic membranes or inorganic materials. They have very high chemical, thermal and mechanical stabilities. So, what happens actually in many applications we need to go for higher pressure. So, when you go for very high pressure applications such as your reverse osmosis for actually desalination purposes, then the membrane should be able to withstand that type of higher pressure. So, basically mechanical, and many a times we need also process certain streams which are coming out of the let us say refineries or such any other process and are at elevated temperature, that means higher temperature, let us say 100 degree, 200 degree, even more than that. Then in such cases certain polymeric membranes are not able to withstand this higher temperature. Actually, due to these two main things, that mechanical stability and thermal stability and low flux problems also associated with polymeric membrane. So, ceramic membranes has come into picture. So, inorganic membranes suitable for use in harsh condition such as corrosive and high temperature environments. Hence, compared to polymeric membranes, inorganic membranes has more advantages, but it is not always true that in for any application we will use inorganic membranes. Their high cost actually restrict the use of such membranes. So, polymeric membranes are also extremely good, however, they have certain problems. So, inorganic membranes have tried to overcome these problems. We will see and discuss in detail what are all these things. So, just a small comparison between polymeric and inorganic membranes. The materials are basically we have discussed in last lecture, polysulfone, then PVDA, PTFE. For inorganic membranes, the materials can be glass, ceramic, silica, titanium, zirconium, all these things. So, the advantages in polymeric membrane is that the cost is very less. If you compare directly with the ceramic membranes, the cost of polymeric membranes are much less. They have a good selectivity and easy to manufacture, and the processability is very easy in case of polymeric membrane. And the advantages of inorganic membrane that they can withstand harsh chemicals, high temperature. So, ability to be sterilized and autoclaved and wear resistant. So, let us say I am using these membranes for certain applications in pharmaceutical or biotechnology industries, in which once the membrane is being used I need to sterilize it. So, for sterilization I have to autoclave it. So, autoclave means it is high temperature and pressure, which many times polymeric membranes are not able to withstand. And narrow pore size distribution and higher porosity which exist in ceramic membranes, thus they have higher flux and better separation features compared to the polymeric membranes. And of course, their chemical stability is also very high compared to the polymeric membranes, and they have a long lifetime also. So, usually the higher hydrophilicity resulting in high fluxes at low pressure. So, most of the ceramic membranes are hydrophilic. So, that is why the flux is actually high at low pressure. So, to increase the flux we do not have to go for a very high pressure. So, the disadvantages in polymeric membrane is this: fouling is a common disadvantage, and then non-resistance to chemicals, limiting operating temperature and pressure, and short membrane life. All these things are been tried to cover up by this our ceramic membranes. However, they have certain disadvantages also. The most important disadvantage are two. One is high cost. The cost is of course as of now with latest development in ceramic membranes, I am hopeful that the cost will come down drastically. And brittleness is another membrane. You need to handle it very carefully, otherwise it will break. And another problem is low membrane surface per module volume. So, per module the module which is housing the membrane, so the surface area actually less and poor reproducibility. So, inorganic membranes refer to membranes made up of materials such as ceramic, carbon, silica, zeolite and various oxides like alumina, titania, zirconia, and also metals such as palladium, silver and their alloys. So, inorganic membranes can be classified into two major categories. So, based on structure, which is this classification is based on structure itself. We can classify of course according to other things we have seen in earlier classes. So, based on structure it can be either porous inorganic membranes or dense, that is non-porous inorganic membranes. So, microporous inorganic membranes have two different structures. So, porous inorganic membranes, either it can be symmetric inorganic membranes or asymmetric inorganic membranes. So, this is true for both amorphous and crystalline membranes. So, please closely look at this particular slide. So, you can see that the top one, the A1, these are all micrographs of scanning electron microscope. So, the first one is a porous membrane. So, we have a top layer there is an intermediate layer. So, we have a top layer here, okay. We have an intermediate layer, this is the intermediate layer, and we have a support which starts from here. So, you can see there are three distinct layers here, it is a porous membrane. So, the B is a dense membrane. This is a dense membrane in which we have a alumina support and the top layer is a LTA layer. It is a zeolite basically. Then the third is asymmetric membrane. It is a clear structure where you can say the distinct pores can be seen here, and it is a double layer of membrane. So, it is asymmetric membrane actually C1. In which we can see there are two distinct layers here, one is here and one is here. So, this is asymmetric membrane and the pores are clearly visible, and the last one is symmetric inorganic membrane in which there is only one layer of membrane, okay, and the pores are also very clearly visible. And so, we just understand that from this particular slide that we can make porous or non-porous membranes of different configurations, either symmetric or asymmetric, using the various ceramic membranes. So, microporous inorganic membranes can be obtained by coating of a porous support with a colloidal solution, it is called actually sol. So, there is a process called sol gel process, which is one of the most important breakthrough in preparing these ceramic membranes, inorganic membranes. This process we will discuss in detail when we will discuss the different methods to prepare membranes. So, as of now let us understand that the sol can consist of either dense spherical particles, that is basically colloids of oxides such as alumina, silicon dioxide or zirconium oxide or polymeric macromolecules. So, coating material and thickness mainly depends upon the application. It is your intended application or targeted applications. Based on that only you can decide what is the type of coating material you want to use and what thickness you will want to keep. So, as you understand that more the thickness, more will be the membrane resistance or resistance to flow. So, that will create problem. So, please look into this particular figure. This figure is a polysulfone hollow fiber membrane for controlled insulin release. This is taken from a manuscript, okay. And the next figure is all about alumina hollow fiber membrane with an asymmetric hierarchical cross section obtained by spinning. So, by spinning method this particular membrane was manufactured. Here you can see the entire membrane how it looks like. It is a hollow fiber membrane, and B is the partial cross section, here the cross section. So, that means this is what you are seeing here, okay, is being projected here in a higher resolution. Then C is the inner surface, okay. So, inner surface means this surface, okay, and then D is the outer surface. So, outer surface means this surface. So, these are the scanning electron microscope images which tells us about how the particular membranes are being prepared and how they look like when you go for a electron microscopic image. So, another example where you can clearly see this is actually MOF framework. MOF stands for a metal organic framework of type ZIF8 layer on asymmetric graded titanium support. So, this support you can see. Okay. So, this is made up of titanium support and this particular layer from here to here. Okay. So, this is ZIF8 layer and you can see this side under B image. So, it tells about the principle of a supported membrane and you can see that the micron thick separation layer is deposited on a microporous ceramic or metallic support. So, this is the separation layer. So, this red one you can see. So, this is the separation layer, actually this will do the separation and this is made up of either zeolite, metal, ionic liquid or MOF by Sol-Gel method usually. Then the second layer where we can see here, it is a true it is a ultrafiltration layer. Third layer again here. So, this is a microfiltration layer. Then we have a coarse support. So, basically it can be a more microporous layer. So, this particular structure is a hierarchical asymmetric inorganic membrane which tells us that we can have more than 3 or 4 different types of distinct layers fused together to prepare a particular inorganic membrane for a particular applications. So, the next slide is basically tells us about the inorganic materials, okay, and their properties. So, most of the inorganic membranes are inert to common chemicals and solvents. So, what is the inherent meaning of this particular sentence is that, so it can withstand acidic and alkali conditions. It should not be exposed to strong acid for long time, though it can withstand acids and alkalis, but if you are exposing the ceramic materials for a long time, then they will start corroding. So, very few chemicals actually bothers to membranes. So, hydrochloric acid and in case of aluminum membrane, it is phosphoric acid, that is the simply no for this two types of membranes. So, acids and alkali are usually used for membrane cleaning, however, they are used in a dilute form. No concentrated acids or alkali are ever used to clean the membranes. So, there is no question of any resistance when you are dealing with a dilute acid or dilute base. So, the ability to tolerate strong doses of chlorine, that is another important features of these ceramic materials. Chlorine at alkali pH is an extremely effective as a cleaning agent. So, all these properties also makes the ceramic membrane more interesting and for applications to harsh conditions. Then the next property is wide temperature limits. So, inorganic membranes can withstand up to more than 350 degree centigrade temperature, 500, 600 also. So, uncontrolled heating and cooling will result in thermal shocks and possible crack, thereby damaging the element. If you are not doing the thermal treatment or thermal procedure, either you are cooling it or you are heating it in a proper or controlled manner, then there will be shocks for the membrane and they will actually develop cracks under this thermal shock, which is not good for the membrane life. Then these materials can withstand wide pH limits. So, it can withstand a pH of 0 to 14. However, some inorganic materials have some limitations. The next one is the pressure limits. So, pressure can be applied almost up to 100 psi, even little more than that also. And however, the type of hosing and sealing that is actually used to hold this membrane inside a membrane module plays a very important role in deciding what type of membrane pressure can be applied for a particular membrane system and a module. So, operating lifetimes. So, many ceramic membranes actually operate for 10 to 14 years, it is a pretty long time. You cannot imagine this for any polymeric membrane, whatever polymeric membrane you can talk of, no polymeric membrane will give such a long lifetime. And inorganic membranes tolerate aggressive chemicals, after washing membrane gives better performance. So, obviously any membrane, whether it is polymeric or inorganic ceramic membrane, we need to wash the membrane because of the concentration polarization, fouling, both external fouling and internal fouling. So, we need to wash it. Okay. So, once you wash, the performance of membranes actually increases. So, washing is very easy in case of ceramic membrane, that is what is the message actually, and polymeric membrane, the washing is little has to be done in a very carefully or controlled manner, whereas ceramic membranes it is easy. Then back flushing capability, this is what I was talking about actually washing. So, it means pressure from the permeate side to feed or retentate side. You can see actually this is the fouling layer which is getting deposited on the surface of the membrane, and these are the pores, and this is actually membrane material. Okay. So, this is feed side and this is permeate side. So, when the process is getting carried out, so feed is here. So, feed will get will be the feed the solute will be separated, and then the separation takes place in this way, and we get a permeate in permeate side. So, when we are doing actually back flushing or back washing, so the name indicates the name itself indicate that we are washing from the back side of the membrane, that feed from the permeate side of the membrane. So, this back pressure lift up some of the accumulated solids, thus improve the flux. So, many times as I told, the solids are getting deposited on the pore of the membrane as well as here also is there. So, when you are doing back flushing, usually water is being used at a certain pressure. So, under this pressurized condition, water will wash away these solids which are deposited inside the pores as well as on the surface of the membrane. And for effective back wash, permeate pressure should be higher than the feed pressure. So, the permeate side pressure should be higher than the feed side pressure, then only back washer will be effective. And most tubular inorganic membranes are well suited for back flushing and back washing. So, most of the inorganic membranes, whether it is a flat sheet membrane or whether it is a tubular membrane, actually most of the ceramic membranes are they are tubular. So, it is very easy to do back flushing as they can withstand higher pressure. So, again let us just quickly go through the advantages and disadvantages of the inorganic membranes. Just in a nutshell, we will again try to recapture what we discussed. So, it has high thermal stability, that is it can we can go for high temperature operations such as membrane reactors and in certain situations. Then it can withstand high chemical stability, pH, corrosion resistance to most of the organic solvents, then well stable pore size. So, biocompatibility and pharmaceutical and food industry, then high pressures it can withstand. Dense membranes have high selectivity separation towards gas separation. So, like ceramic membranes are very good for the gas separation applications as well as for evaporation. So, selective separation of gases can be done by this by such membranes, and they have more mechanical strength as well as long lifetime. But again they have some disadvantages too. It is not that their ceramic membranes are win-win for all cases or all situations. So, the most important disadvantages as to the two which I told you, one is high capital cost, second is brittleness, and then it is difficult to prepare membranes. It is not so easy. Polymeric membranes are easy to prepare, and it is difficult to handling at high temperatures. So, when you go for this module packing, then leakages will be there, probabilities always remain for such ceramic membranes. Then low permeability at high selective separations, then difficult to scale up and poor reproducibility. So, these two are limiting their application in certain areas. Actually, scale up is very important when you go for designing of such systems for a large scale applications, and reproducibility also very important, because unless until the membranes and their composition is reproducible and are giving more or less the same performance, then commercially it is not feasible to manufacture them. So, let us look at some of the inorganic membranes or the various types of inorganic membranes that are available commercially. So, the first one is ceramic membranes. This you can see from the image. So, these are actually tubular ceramic membranes. Okay. Then we have glass membranes. Glass membranes are having lot of applications also. We will see in our subsequent discussion. Then we have metallic membranes like stainless steel membranes and other metallic membranes, and we have zeolite membranes. So, zeolites are very interesting class of materials and have wide range applications from catalysts and adsorbents to and as well as membranes. So, there are different types of materials, we will see one by one. The first one is ceramic membranes. So, various types of metal oxides like alumina and zirconia are used. There are many others also. They are not limited to these two, there are many others, just I have shown two, and they are prepared by sintering or sol gel process. Then we have glass membranes. So, silicon oxide or silica, which is silicon dioxide, is essentially used to prepare glass membranes. So, they are prepared by leaching on demixed glasses. Then we have metallic membranes like palladium and silver coated metallic membranes. We have stainless steel metallic membranes, and then we have zeolite membranes. So, zeolite membranes ZSM 5 and silicalat 1 or narrow pores, and they are used actually for the gas separation applications. So, ceramic membranes are very new to the membrane science actually, and since last a decade or so, they have been commercialized, and now they have wide range applications, whether it is water wastewater treatment or they are used in membrane reactors for carrying out certain chemical reactions under controlled conditions, and even pharmaceutical and biopharmaceutical industries also. So, most of the produced ceramic membranes are usually in the ultrafiltration and microfiltration range. This is another limiting applications actually. So, we hardly can produce nanofiltration or RO membranes using ceramic materials. So, pore diameter of microfiltration and ultrafiltration ranges from 0.01 to 10 micron. Generally, ceramic membranes are made by slip coating sintering procedure to get usually MF and UF pore sizes. Sol gel method is used to get pore from 10 angstrom to 100 angstrom. So, microporous ceramic membranes are manufactured from inert materials. So, we can have aluminum based ceramic membrane, we can have either titanium based or we can have silicon oxides based. So, ceramic microfiltration and ultrafiltration membranes particularly suitable for food and pharmaceutical applications, in which membranes require repeated steam sterilization and cleaning with aggressive chemicals, because they are for human consumption anyway. So, you have to be very careful about the sterilization processes, which is basically done using autoclaves. So, these inert materials are stable at high temperature and harsh chemicals, high pressure application and conditions under which polymeric membranes usually fail. So, polymer coated ceramic membranes are also used and developed, and they are especially used in water and wastewater treatment applications. So, this you can see this particular scheme tells us about it is a ceramic membrane hollow fiber membranes. So, this is a single unit of a hollow fiber membrane. So, you can fuse together many such membranes and housed in a particular module. So, then this looks something like this. So, let us carefully look at this particular slide which tells us about the hollow fiber ceramic membrane and its scanning electron micrograph image, actually micrograph. So, you can see how the membrane actually looks like. So, you can see this is the area, okay, this area, particular area where it is in, this is the mesoporous intermediate layer, right. So, then we can have the macroporous support, which is this area, this white portion you are seeing. So, this area is the macroporous support, right. Then we have this layer which is microporous top layer, okay, which is this particular sections, these areas, okay. So, and this is what is the microporous layer, actually that is doing the separation. So, feed is actually flowing inside this one particular hollow fiber tube. So, you can send feed from this side, okay, and they are flowing, you can see they are flowing here inside the tubes, okay, and permeate is getting out here, okay, and you can get the retentate here directly coming from inside. So, the feed is flowing in the lumen or the pores, okay, the hollow fibers, this one the hollow ceramic membranes inside the hollow ceramic membranes, and the permeate is coming out through the macroporous support layer here, okay. So, let us quickly go through the material properties of the ceramic membranes. So, thermal stability, that there are very specific properties of the ceramics originated from their electronic behavior. The melting points are very high and reach can almost 4000 degrees centigrade. The high temperature resistant make these materials very attractive for gas separation. As I told you in the beginning also, due to this their thermal resistance, so they are extremely good for gas separation application as well as pervaporation also. So, you can see some of the melting points of these ceramic membranes. Alumina is 2050, zirconia is 2770, these are all in degree centigrades. Titanium is 1605 and silicon carbide is higher, 2500. Then chemical stability. The chemical stability of inorganic materials is superior than the existing polymeric membranes with respect to pH and organic liquids, widely used in the field of microfiltration and ultrafiltration, especially in harsh environment. So, all kinds of cleaning agents can be used, allowing strong acid and alkali treatment also. However, actually for cleaning purposes, dilute acids and dilute alkalis are being used. So, lifetime of ceramic membrane is anyway greater than the polymeric membranes. So, then mechanical stability are considered in those applications involving high pressure or self supporting materials. So, ceramics are characterized as hard and brittle materials with a high elastic modulus. So, you can see this stress strain curve of alumina and of PMMA, which is polymethyl methyl cryolate, which is given below in this particular stress and strain curve. What it says that when you add the PMMM to 5 weight percent nano alumina, then its stress strain relative seems that is actually has been increased to 604. So, you can the 600% increase in the strain to failure and the appearance of a well defined yield point when tested in a uniaxial tension. So, this particular slide tells us that the properties, the strain to failure properties actually increased when you add nano alumina materials to the polymethyl methyl cryolate materials. So, then the next was is the glass membranes. So, glass membranes are nothing but porous glass. The pore size actually ranged from 0.3 nanometer to 1000 nanometer. So, general glass membrane composition is this: silicon dioxide 70%, boron trioxide 23% and sodium oxide 7%. This is a general composition. However, the composition also varies for different glass materials. They are actually optimized to suit a particular application. Then produced by phase separation and leaching of alkali rich borate phase. So, it is prepared by phase separation process in which silicon dioxide rich phase remains and the boron trioxide rich phase is leached out. So, this particular phase has been leached out from this particular composition. So, pore size can be controlled by temperature. So, and we get a very narrow pore size distribution and glass membranes can be modified easily. It is easy to prepare actually. So, the properties are thermal and chemical stability or resistance higher, then optical transparency is there, that is another important thing when you go for some applications in which you need to understand and visually see what is happening inside it. Then better access to the active sites present inside the pores, high permeability and selectivity for chlorine. So, they can withstand higher chlorine concentration if it is present in the stream. Then application is in gas detector, catalyst support and gas separation. You can see one typical hollow fiber glass membrane, this is of around 10 micron image this is. So, next is the metallic membranes. So, these are dense metallic membranes are typified by palladium and silver membranes. So, metallic membranes are not limited to palladium and silver, there are many, but these are widely used. So, palladium membranes are exclusively been prepared for hydrogen permeation and silver membrane for oxygen permeation. And they are selective membranes actually, palladium coated membranes for selective membrane for hydrogen permeation and silver coated selective membranes for oxygen permeation. And they are prepared by cold rolling, electrolysis plating, electroplating, chemical vapor decomposition which is called CVD or magnetron sputtering method. So, the properties are they are highly selective, but and better mechanical and thermal stability as well as they have a very long life. So, applications are membrane reactors and gas separation. This particular image shows a stainless steel membrane. So, let us see how hydrogen permeation actually happening using this particular palladium based membrane. You can see from a composition of gases which is there in the feed side, this is the feed side. And what is our intended application? Intended application is to selectively permeate hydrogen, so that we get a pure hydrogen on the permeate side. So, the a particular membrane which is being prepared, which is palladium based membrane, what it will do actually. So, first the hydrogen molecule is absorbed on the membrane surface, here they are getting absorbed on the surface of the membrane. So, when they absorb, what is happening? So, the hydrogen is dissociating into hydrogen atoms, right. So, after the dissociation every individual hydrogen atom loses its electron to the metal lattice and diffuses through the lattice as an ion. So, now they will diffuse through. Okay. So, then once they diffuse across the membrane and reaches the permeate side. So, the hydrogen atoms emerging at permeate side of the membrane again reassociate themselves to form hydrogen molecule. Okay. So, once they come here again they reassociate to become hydrogen. Okay. Then dissolve and complete permeation process starts. So, the membrane is made in such a way that it will selectively only permeate hydrogen in the form of hydrogen atoms. Okay. And then once they come into the permeate side, these hydrogen atoms will reassociate to form the hydrogen molecule. And similarly, oxygen selective membranes and other gases selective membranes such as carbon dioxide selective membranes are also being prepared. So, palladium membranes show high solubility and permeability for hydrogen. I am talking about this particular application which we just discussed. Then in 1950s and 60s, palladium membranes show 99.9% pure hydrogen separation using a 25 micron thick membrane. So, the advantage is high hydrogen selectivity and a long life of course, and disadvantages it is extremely expensive, almost 100 times more expensive than any polymeric membrane, and it is brittleness. Then palladium and silver alloy used to reduce cost and increase toughness. So, to increase to reduce the palladium membrane cost, silver has been added, okay, and alloy has been prepared. So, it has reduced the cost as well increase the toughness. So, this particular palladium silver alloy shows low permeability, and to avoid all these problems composite metallic membranes are nowadays prepared. So, a composite membrane with a very thin metal layer will give a better separation. Why thin layer? Because thin layer will provide less resistance to the transport of the solutes. So, thin layer of palladium either on tantalum or vanadium support film on porous Dept is usually prepared such as ceramic or stainless steel. The tantalum and vanadium are quite permeable to hydrogen. So, possibility of getting more hydrogen. So, this is why actually the reason why tantalum and vanadium are particularly chosen. So, these membranes are quite permeable at high temperature. So, they will reduce the overall material cost and improve the overall mechanical strength. Now, let us come to the important class of ceramic membranes which are called zeolite membranes. So, zeolites are very interesting materials. So, zeolite membranes are latest in the inorganic membrane series. So, zeolites, what are zeolites? So, they are silicate or alumni-silicate materials formed from a 3-dimensional network of silicate, aluminate, tetrahedra. Okay. And these tetrahedras are linked by oxygen atoms to form the cases. Okay. So, you can see how it looks like in a particular this is a case. Okay. So, in a zeolite structure these individual cases are linked together in various geometries that forms the pores actually, okay, with defined regular shapes and sizes. So, zeolites occur naturally, but are produced industrially on a large scale also synthetically. So, there are about 240 known zeolite structures, out of that almost close to 40 are natural among them. So, you can see this particular image, it is a natural zeolite, it is Thompsonite. This is one of the rarest zeolites which is found in India. Okay. Here you can see this is a ZSM 5, okay. This is a commercial zeolite, synthetic and prepared synthetically. So, sodalite beta case can form several structures with pore ranging from 3 angstrom to 8 angstrom, okay, and pores are uniforms. So, you can see this is a particular beta case, sodalite case. Okay. So, you can see this is your silicon, aluminum and oxygen, okay, they are present. Okay. You can see this is actually silicon, okay, then this is aluminum and this is oxygen. Okay. So, they are present in such a way that they form cases which are called these beta cases, sodalite cases. Okay. And in aluminosilicate structure they carry a negative charge which is usually balanced by the sodium, potassium or calcium counter ions. So, fine tuning of the pore opening of zeolite structure is possibly done by exchanging potassium or calcium for sodium counter ions. So, this particular slide tells us about different types of zeolite membranes, okay, and how and about their pores dimension. So, the first one is fossa site. Okay. You can see the dimensions of the pores is actually 0.74 nanometer, to 1.3 nanometer, and the next one is this is ZSM-12. Okay. The structure is something looks like this, okay, and they have this cylindrical types of pores of 0.57 nanometer pore diameter. Then the next one is ZSM-5, another class of ZSM membrane. Okay. In the presence of silicate 1 actually. So, it has a pore structure of again cylindrical pores arranged in a very different way. The pore size is usually 0.456 nanometer, and the next one is theta 1. It's a ZSM-22 zeolite. Okay, its pore size, pores are also again cylindrical, and 0.45 nanometer is the pore size. So, zeolite membranes can be formed on microporous membrane by using a in situ hydrothermal synthesis technique. Membranes can be prepared by deep or spin coating, sputtering, chemical vapor decomposition or laser ablation. So, the properties are that they work at very high or elevated pressure temperature, they can withstand harsh acidic and base conditions, and they are hydrophilic or hydrophilic both in nature. So, you can choose zeolites in such a way that either we can target at a hydrophilic membrane or a hydrophobic membrane. So, the unique property is that they is something called molecular sieving. So, different molecules can be sieved using particular types of membrane, so as to get a easy separation, and they have selective sorption as well as they have catalytic activity. So, due to this catalytic activity they are used in the catalytic membrane reactors. Okay. Application is gas separation, pervaporation and catalytic reactor. So, the next class of material is alumina. So, alumina is aluminum oxide, is a amphoteric oxide of aluminum with the chemical formula of Al2O3 and commonly called as alumina. So, relatively high thermal conductivity for a ceramic material, and properties are that its melting point is very high, 2072 degree centigrade, and they are highly refractory and they have high wear resistance. Okay. So, you can see how the crystal structure of alumina looks like, and this is a ore of the alumina from which alumina actually is being prepared. So, the next class is zirconia or zirconium. So, it is basically zirconium oxide, is the oxide of zirconium with the chemical formula ZrO2 and commonly called zirconia. So, it has the highest strength and toughness at room temperature compared to any advanced materials. This is why this is very interesting for high pressure applications, and the properties are high resistance to corrosion, wear and abrasion, resistance to crack formation. You can see how the zirconium molecules are actually networked together. So, with this type of bonding actually, this is the reason why they give a very higher mechanical strength. The next class is titania. Titanium dioxide or is the oxide of titanium with the chemical formula TiO2 and commonly called titanium. So, titanium dioxide is commercially available in two crystal structures, one is anatase and another is rutile. So, rutile titanium oxide pigments are preferred because they scatter light more efficiently and are more stable and are more durable than anatase. So, the properties are chemical and mechanical higher resistance, it imparts something called a glaziness. You can see from this particular image the ore of the titania also itself also looking so glazed, and it for non-toxic environment this is used, and it can withstand wide range of pH. So, this is the crystal structure of how titania actually looks like. So, let us just quickly go through and understand how ceramic membranes are prepared. We will discuss this in future classes. Okay. So, once you choose the materials, so you basically choose the choice of inorganic powder from which you want to prepare the membrane, and you have to add two things apart from other smaller things. The two major things, one is called pore former and another is called binder. So, pore former are certain agents which helps in forming the pores. Okay. So, actually they degrade and form pores, and binders are the materials which will bind together this inorganic powders, pore formers and other materials together. You need some binding agent to bind. Okay. Apart from water, of course, will be used to prepare the composition. So, you can then you go for the powder preparation. So, you can mix the powders and then you go for milling. Then the temperature treatment like drying, calcination, sintering will be there, and their final layer deposition, which can be done by either by sol gel method or by CVD method, or you can use carbon zeolite on metals, any these type of materials. So, let us just quickly go through what is the role of binders and plasticizers. So, during membrane preparation, some inorganic binders are often added to the salt to prevent crack formation in the initial drying process. So, this is very important, because once the crack forms, you cannot further go for the membrane preparation, you have to stop it. So, polyvinyl alcohol, cellulosic compounds and polyglycol compounds are usually used as binders. So, mostly PVA and PEG are being used. So, plasticizers are the materials which used to reduce the brittleness. So, as you know, ceramic membranes are highly brittle. Just to decrease the brittleness, some plasticizers are being used. So, they are actually burned up during the heat treatment process. The possibility of preparing membranes having no defects by adjusting the added amount of binder or plasticizer like PVA are already being tested. The goal is to develop a membrane with a high surface area and well defined pore size distribution as a blank alumina, but without any cracking. So, the next is the role of pore former or pore generator. So, pore forming agents like starch are used while preparing ceramic membranes. We have many more materials. Starch is also being used. Starch or amylum is a polymeric carbohydrate consisting of numerous glucose units joined by glycosidic bonds. So, this polysaccharide is produced by most of the plants, and it is most common carbohydrate in human diets and is present in large amounts in staple foods like potatoes, wheat, maize, that is corn, and rice, etc. And the average pore size and porosity of the ceramic membrane supports were improved by adding cornstarch. So, with this we come to the conclusion of this lectures, wherein we have understand what is the ceramic membranes, how they are prepared, and what is their properties, advantages and disadvantages. So, before we wind up, we will just quickly go through this particular slide, where this tells us about the different types of commercially available inorganic membranes. So, these the first column tells us about the manufacturer, the name of the manufacturers. You can see the different companies like DuPont, NGK, then TDK, okay, and the trade name. The next column is the trade name of the membrane. So, let us see the first one, which is called Membralox. Okay. So, the membrane material is here zirconium oxide, dioxide, alumina, and the support material is again alumina. The membrane pore diameter ranges in the 200 to 100 nanometer, 0.2 to 5 micrometer, and that particular range. Okay. The geometry of the substance, geometry of the membrane element is actually monolith or tubular type, and the tube or channel inside diameter is 4 to 6 mm. Now, these particular tube diameters on this can be varied also, and this tells us about that we have huge number of companies. They are actually, the list is more. So, I have just tried to show some of these commercial membranes. There are many companies across the globe which are preparing these ceramic membranes, and they are excellent in performance. Okay. Before we wind up this particular let us quickly glance through what we have discussed since last 3-4 lectures. Okay. So, we have discussed about the membrane basics. We have tried to understand how separation takes place using different type of membrane, okay, and different types of membrane classification and various processes. So, this next 2 slides, this slide and the next slide, we will just quickly glance through what we have understood. So, this is again I am just trying to group everything in a single slide. So, in which this it tells us about the classification and characteristics of membrane processes. The first column based on the driving forces. So, we can have either pressure difference as the driving force, or concentration difference, electrical potential difference, or temperature. So, under pressure difference we have microfiltration, ultrafiltration, nanofiltration, reverse osmosis, and pervaporation. So, as you go from microfiltration to RO and PV, okay, the pore size actually decreases. However, the pressure that is required for separation is increases. Okay. So, the type of membrane is that we can prepare is symmetric microporous. Either we can have asymmetric microporous membrane also, we can have thin film membrane also, which is again anisotropic membrane, and we can have asymmetric skin type of membrane, okay, or homogeneous polymer type of membranes. So, all these possibilities are there using polymeric membranes. Then the applications is actually in water and wastewater treatment. Desalination is one of the most important application, okay, and it we can go for fractionation of macromolecules also. Then in the concentration driven process, either we have diffusion dialysis or membrane extraction, okay. So, we can use both non-porous or microporous membrane as the case may be. So, under electrical difference potential difference we have electrodialysis. Okay. So, the permeate is actually ionized solution water and the retentate is non-ionic solutes. Okay. Ion exchange are the membranes which are used for this electrodialysis purpose. So, we have cation exchange membrane, we have anion exchange membrane and we have bipolar membrane also, having both fixed cation and anions imparted on that particular membrane. Then under temperature difference we have membrane distillation. Here we separate solutes which are less than 1 nanometer, it comes to the retentate side, okay, and usually microporous membranes are being utilized for these purposes. And let us quickly go through the different applications once again, though we have discussed in last few classes. So, in microfiltration, the wastewater treatment, membrane bioreactor, sugar, fruit, wine, tea industry, okay, fermentation, broth concentration, all these things are typical applications of microfiltration. So, similar applications are also can be done by ultrafiltration, okay, and we can use also for ultrafiltration for the separation of proteins and enzymes and antibodies. So, then nanofiltration which is being utilized for drinking water, wastewater treatment purposes, as well as sugar and tea industry and dye removal for textile effluents. Then reverse osmosis, the classical example is of course the desalination and drinking water preparation. Then wastewater treatment of course, then it can be used in dairy and fruit vegetable industries, wine and sugar industries, as well as heavy metal removal from various effluents. Then gas separation, under gas separation we can have hydrogen recovery, we can have carbon dioxide separation, we can go for nitrogen enrichment, and there are several applications. Under pervaporation we can go for ethanol dehydration, organic material. If you remember that making alcohol free beer is another application of using pervaporation membrane. Then using electrodialysis we can again go for this desalination process, the demineralized water, wastewater treatment and dairy and sugar industries. So, we have come to the conclusion of today's class. So, as usual again I am showing you this the slide which containing the different names of the books, okay, for the text and reference purposes. So, you can refer them for some of the materials. So, most of the materials are taken from these books. Then in the next class, so that will be the module 2 and lecture 5, we will discuss what are the different types of membrane modules, what is a membrane module, what are the different types of membrane modules exist. So, we will discuss in detail about plate and frame, tubular, spiral wound and hollow fiber and other materials, and what are the different types of flow types that is happening inside the membrane module, as well as how we will select a particular membrane. That is also very important. We need to understand how to select a particular membrane module, membrane as well as membrane module. So, thank you very much, and if you have any query, please feel free to write to me at kmohanty@iitg.ac.in. Thank you very much.